Welcome everyone to this session on operating and supporting Delta Lake in production. My name is Harikrishnan Kunnimvettil and I am a Senior Technical Solutions Engineer at Databricks. My co-speaker today is Madan Pillai. He is also a Senior Technical Solutions Engineer at Databricks. So let's get started with the agenda. So in the first half, I'm going to discuss about the various operations or commands that are available in Delta to organize and store your data efficiently. Then we will also discuss about some frequently asked questions from our users like what operation should I run for my workload, or what should be the frequency, or what type of cluster resource to be used, etc. In the second half, Madan is going to discuss more about the metadata part, the importance of metadata, the various files we store as part of the Delta log, and we will also discuss about some configurations and common exception. And to finally wrap it up, we will have some tips and tricks that can help you to work on Delta tables. Okay, so when it comes to the data part, there are four main operations. The first one is the optimize operation. The optimize is also called as bin packing or compaction. This is one way how Delta handles the large number of small file problem. So in bin packing, what we do is that we coalesce or combine the smaller files into larger files. And the larger files will be of the size 1 gig or 10 million record, whichever it hits the first. So this operation is idempotent, which means if you run the optimize query twice on a Delta table, the second run would not have any effect. So assume that you have around 10.5 gig data in your Delta table. And when you run an optimized query, we are going to create 10 1 gig files, and one file will be around 512. So these 10 files which are already optimized would not participate in any further optimize operation. That means, say, you are adding some more new data to your Delta table, and then you are running another optimized query. So this 512 MB file would definitely participate in the further optimize operation, but the files which are already hit the limit of 1 gig or 10 million records would not participate in further optimize operations. So the optimized query has a optional parameter to specify the columns. This is where the Z order comes. So the Z order helps in data skipping. Internally, we use the Z order spatial curve principles. So there are other curves like Hilbert curve, which we have implemented and it is in preview mode. And for the internal implementation, we use a range partitioner. And we have seen that users who have optimize and Z order on their Delta table, their read queries are much faster. And unlike the normal optimize operation, the Z order is not idempotent. Say you have a Delta table, now you run an optimize with Z order. It will pick all the existing files and rewrite those into optimized files. These optimized files are tagged to a logical entity called Z cube, and the maximum size of a Z cube is 100 gig. Assume that you are now adding more data to your Delta table, and then you are running another Z order query. So the first thing we will check is that whether the Z cube size is 100 gig. That is the data volume of the currently optimized files is 100 gig. If it is less than 100 gig, then the newly added data and the existing data is completely rewritten to ensure the co-locality of the data. And assume that if you are already hit the 100 gig limit, then a new Z cube is created. This can be configurable, but we recommend sticking with the default. So the optimize and the optimize with Z order helps in rewriting the data once the write operation is completed, and it efficiently rewrites the data. Now, what if you want to improve the write operation itself? That is where the optimized write will come into action. The optimized write will introduce an extra shuffle step, and it will create less number of files. We have seen some users unintentionally referring it as auto optimize. Actually, auto optimize is a Delta feature and it has two parts, optimized write and auto compaction. So optimized write is just one part of the auto optimize feature of Delta table. And with the regular optimize operation, we create size of the order of 1 gig. Whereas with optimized write, we create files of the order of 128 MB. One thing to note here is that this limit of 128 MB is not a hard limit. We actually control the amount of row compressed data that one task is handling, and that will be around 512 MB by default. Based upon the nature of the compression of your data, the final file size could change. But generally, we have seen 512 MB of data when stored with Parquet and Snappy compression, it will be around 128 MB. So the last operation here is about the auto compaction. As we discussed for Delta, we have the auto optimize feature and auto compaction is one among that. Auto compaction, you can actually think as a miniature version of the normal optimize operation itself. Instead of creating files of the order of 1 gig, here the file size will be 128 MB. So the main difference is that you do not have to run an auto compaction because auto compaction is kicked off once a write operation is completed. That is, once the write is completed, we check for certain conditions. Conditions like does that directory, the partition directory or the table directory has at least 50 files which are less than 128 MB. If it has, then we pick all those files, do a bin packing, and create larger files of the order of 128 MB. Okay, so now we have discussed the various commands and operations you can run on your Delta table. Now the question is that what operation should I run for my use case? So one common question what we get from our users is that is running optimized write a good choice on streaming workload? So we have already seen that when you use optimized write, it introduces an extra shuffle step. So definitely your micro batch execution time is going to be more. But if your streaming workload has SLA to accommodate that extra shuffle step, then definitely it's a good idea to turn on optimized write for streaming workloads. We know that having optimized writes can actually help to improve the read performance. It should be also noted that having optimized write can actually help to reduce the time spent on your normal optimize and vacuum commands. So the regular optimize and vacuum commands now has to deal with less number of files, so it's going to be more faster. And we had a customer who had more than 3 petabytes of data, and there were almost 400 terabytes of data getting added every day. And they were running optimized queries continuously to have better read performance. But the optimized query was running more than 6 to 8 hours because of the fact it had large number of files. When this customer turned on optimized write, we could see that the regular optimized operation was taking much lesser. Again, this is because of the fact we are dealing with less number of files. One other common use case is that the map only write operation, where you are reading the input data and just performing some transformation and writing it to Delta table. Usually such use cases can have large number of files, and having having an optimized write can actually help you to reduce the number of files. One other question what we get from our users is about the Z order and partition by. Both are actually both actually help with the data skipping. Then which one should I use? Partition by is a great strategy, and it actually helps in data skipping because we do partition pruning. But the columns that you choose for partition by also matters. Say by mistake, if you are choosing a column with high cardinality, then it is possible that you create large number of small files, and that could be problematic. So we had a customer who had more than 300 terabytes of data in a Delta table, and they were having three partitions. That is, they partitioned the Delta table on three columns. And what happened is that it was creating 25 million files. So what we recommended the user was to partition based on two columns, and instead of partitioning on the third column, do Z ordering. And we could see that the number of files actually came down to 650K. Considering the volume of the data, that's a pretty good number. And the read performance was much, much better because of the fact now we are dealing with less number of files. All right. So now that next question is that how should I identify the number of files in a partition to understand whether it is more or less? So this snippet of code can actually help. You just need the location of your Delta table, and you can run this in a notebook, and it will give you the number of files for each and every partition. Okay, so now we discussed about different strategies. Now the question is that when I should run or what frequency I should run these operations. The auto optimize runs on the same cluster, so then there is no question about the frequency. It is triggered after a write operation, or optimize write is triggered while the write is happening. Whereas the optimize and Z order, we can actually control the frequency. So if you want your read operations to be much faster, then you can run the optimized queries frequently. Our general recommendation is that if your table is getting updated frequently, at least run the optimized queries once a day. And if you want better read performance and your priority is not the resource spent on optimize, then you can increase the resources. And we had some use cases from our users, like they are actively writing to a table partition each day, but their downstream will consume it maybe on the next day. That is, there is no active read happening on the partition where the write is happening. For such use cases, if you have Z ordering, then it's a good idea to delay the Z ordering. Again, this is because of the fact we discussed earlier that Z ordering is not fully idempotent. So coming to the vacuum part now, many users ask us that whether optimize and vacuum should be executed together. Optimize and vacuum are completely independent operations. So there is no reason that I have to run optimize and vacuum together. But again, these are operations that you have to run on your Delta table to for the manageability. For the ease of manageability, so it's a good idea to combine optimize and vacuum into one single notebook job or so. Few things to note about vacuum is that vacuum will clean up the unwanted files from the storage. So vacuum can actually help to save the storage cost. The vacuum operation is done from the Spark driver. That is, initially we list the table and identify the files which are not active. And this is done using a Spark job. But thereafter, the deletion will be done by the Spark driver. And if you want to get an estimate on how many files the vacuum is going to clean up or your current state of Delta table, then we suggest running a vacuum command with the dry run option. So the last part is that where exactly I should run these commands. Again, the auto optimize, that is the optimize write and the auto compaction will be triggered on the same cluster where the write operation is done. Whereas you can choose the cluster type where you run the Z order and the normal optimized queries. One thing to note here is that both of these operations are compute intensive, which means it involves operations like Parquet decoding and encoding. So it's recommended we use compute intensive workloads, or you can also use general purpose instances which has better core to memory ratio. Few other best practices on the optimize is that it's always a good idea to have a where clause and give the required partition where the table is getting updated. And one final note about the vacuum is that when you run vacuum, as we discussed earlier, it runs on the Spark driver. Because of that reason, it's always a good idea to use auto scaling cluster so that the first step we will use the Spark resources to identify the files to be cleaned up, and then the actual cleanup will happen from the Spark driver. That's all I had on the data part. Now Madan is going to discuss about the metadata. Thank you.
Thanks, Hari. Hi, everyone. I am Madan Pillai. I work as Senior Technical Solution Engineer for Databricks. I work in Spark SQL, Delta, structured streaming areas. Today, I'm going to talk about the second half of this session, Delta Lake in production metadata. Here, we are going to look into these topics, a sneak peek into Delta Log. Here, you will see what the Delta Log contains, why we need it. Next, you will see Delta Log configs, two important configuration properties related to Delta Log. Next, you will see Delta exceptions, some of the common exceptions users face due to incorrect design of the workflow. And last, I will tell you about some cool tips and tricks that you can use in your Delta Lake application. Sneak peek into Delta Log. Delta Log tells you who, what, when, and where aspect of your Delta Lake table. Here I am doing a describe history on the Delta table name, and it tells you who, which means username, user ID of the person who performed the commit. It also tells you what aspect of the Delta commit. It tells you whether it is a write operation or is it a merge operation and so on. It also gives you when the commit happened. What is the timestamp? The timestamp is in UTC format. It also tells you where aspect, which means whether the commit happened as part of a notebook. If so, what is the notebook ID? What is the cluster ID of the cluster that performed this commit? Let's take a deep dive into Delta Log. If you ever did a file system listing command on your Delta Lake table, you will see _delta_log folder within that. If you see beneath it, there are a lot of .json and .crc file and some .checkpoint.parquet file. So let's take a deeper look into .json file. Here, what I'm doing is a spark.read.json on one of the JSON file. What it gives me is a data frame, as you see. It has add column, commit info column, and remove column on the far right. Add column tells me what are the list of files added as part of this commit. Commit info is going to tell me who performed this commit, what is the cluster used, what was the operation that performed this commit. And on the far right, you will see remove column. It shows the list of files removed as part of this commit. Next, let's take a look at .crc file. Let's do a file system head command on one of the CRC file, and this is what you will get. You'll see table size in bytes, number of files, num files. So table size in bytes tells you the size in bytes of the table. Num files will give you the number of files added as part of the commit. It also gives other stats like num metadata, num protocol, and num transactions. Next, let's look at .checkpoint.parquet file. You will notice there are less .checkpoint.parquet file when compared to .json and .crc file. This is because we create .checkpoint.parquet file once in every 10 commits, whereas .json and .crc file are created for every commit. Let's take a deeper look on what this .checkpoint.parquet file contains. I'm doing a spark.read.parquet here on this parquet file, and what it gives me is a data frame. It has add and remove column. Add column tells me what are the files added, and remove column tells me what are the list of files that were removed. You may be wondering, even the .json file was giving similar information. How is it different from .json file? Well, the .json file tells you the list of files added and removed as part of that specific commit, whereas this .checkpoint.parquet file is going to give you all the list of files added and removed throughout the history. Why do we need this .checkpoint.parquet file? This is used to compute the latest state of the Delta table. So how do you find what is the most recent .checkpoint.parquet file? If you do a file system listing command on your Delta Lake path, like you will be able to quickly glance and find what is the most recent .checkpoint.parquet file. But how does a Delta table know? For that, we need _lost_checkpoint. That is the next one, _lost_checkpoint, and that is a file. When you do a file system head command on this, like you will get version 10 in this slide. So what it tells is 10 is the most recent .checkpoint.parquet file. So Delta Lake table knows this is the most recent checkpoint.parquet file, and it goes and creates the latest state of the table, and it reads the JSON files after that, and it creates the complete state of the Delta table. So we have seen enough of this Delta log, like the .json file, .crc file, .checkpoint file. You may be wondering, like, how many files do we retain this? Like, is it going to incur storage costs? Is there any way to tweak the number of log files that we maintain? To answer this, like, we have the next topic, which is Delta log configs. Here we have two configuration property. First one is log retention duration. As you see in the slide, delta.checkpoint retention, delta.log retention duration is the property. This determines how long the log files are retained. So if your Delta Lake table has a lot of commits happening, this may result in a lot of log files being maintained. So if you want to reduce the number of log files that we retain, you can always alter the table using the alter table command to reduce it to 7 days or so. So what happens is, like, only 7 days worth of log files are retained. Next, we have another property called checkpoint retention duration. This determines how long the checkpoint files are kept. So by default, like, we maintain only 2 days worth of checkpoint parquet file. Why do we maintain only 2 days worth of checkpoint parquet file? This is because we need only the most recent .checkpoint.parquet file to compute the complete state of the Delta table. If your Delta Lake table is a streaming sync and too many commits are happening, it can result in more checkpoint parquet files being created. In that case, you may need only 1 day worth of checkpoint.parquet file. In that case, you can use the highlighted alter table command to reduce your delta.checkpoint retention duration to 1 day or so. Next is about Delta exception. We have seen some users facing concurrent modification exception while using Delta due to incorrect design of the workflow. So I'd like to explain what this exception is using an analogy. So let's say you are driving a car in freeway. As you have multiple lanes, you can drive in parallel along with other cars. But what happens if you hit a tunnel and there is only one lane? You need to drive one after the other. So this is the same way concurrent modification works. So if you are performing operations on your Delta Lake table across different partitions, you can perform concurrently. But if you are performing operations on the same partition, there are some restrictions in performing concurrently. So this table highlighted, like, will illustrate what two operations can perform on the same partition concurrently without conflicting, and what two operations can conflict when trying to operate concurrently on the same partition. Concurrent append exception is one of the exceptions that you may face when you are trying to add the file to the same partition where your operation is reading. You may get concurrent delete read exception when you try to read a file, whereas a concurrent operation has deleted the file. And you may also see concurrent delete exception if you try to delete a file from a partition and a concurrent operation has already deleted the file. So how do you avoid these issues? So there are a few ways to avoid these issues. Like, the different commands can be combined in a single application, in a single pipeline, and you can sequence it. The other way is you can keep it as different jobs, but you can schedule the jobs one after the other, just like how you go in a tunnel one after the other. The same way, you can schedule your jobs one after the other so that they don't conflict. And the last way is to add retry logic to each of the jobs. In that, like, you can still run concurrently, but what you do is you embed the retry logic in both the jobs. So what happens is, if any of these exception occurs, it will simply retry and you should be good to go. Next, as I promised, I'm going to tell you some cool tips and tricks that you can use in your Delta Lake application. First one is how to find what records were added between two versions of your Delta table. Let's say you have a couple of versions, like, let's take for here as an example Delta table at version 2, and you have Delta table at version 0. Select star from Delta table at v2, except all from Delta table at v0, This is going to give you all the records in Delta table at version 2, but not in Delta table at version 0. Next one is how to find what files were added in a specific version of a Delta table. For this, what you need to do is you need to grab the corresponding JSON file corresponding to that version. You do a spark.read.json on the JSON file. What it gives is a data frame. And then you add a filter where add is not null and select add.path. It's going to give you the list of files added in this specific commit. Next is how to find which Delta commit removed a specific file. This is very instrumental in debugging certain issues. Let's say you are facing file not found exception or file read exception, and let's say the error stack trace is pointing to a specific file, and you may need to find out what happened to this file, like which commit added this file and which commit removed this file. So it's not so easy to find out. So this snippet of code can help you to find which commit removed the file. So what we are doing here is like we are going through a list of versions from the oldest version to the newest version, and we are reading each of the corresponding JSON file and filtering where remove is not null, and we are selecting the list of files that were removed and checking if the given file in question is there. So if it is there, like it will print the version. So basically what it does is it prints the commit version that removed a specific file. That's all for this session. Your feedback is very important to us. Don't forget to rate and review the sessions. We hope you enjoyed the session. Thank you.